Welcome back. In the next part of this lecture, we'll be talking about solving equations that are quadratic in form. And by that I mean that they're not truly quadratic equations. However, with a little bit of a substitution, they could be rewritten as a quadratic equation. So something like this equation that we have here, I mean, technically it's a radical equation, so you could solve it the same way that we did the previous problems. You could isolate the root, square both sides, come up with your solutions. But instead, you might notice that this could be transformed into a quadratic equation, because a quadratic equation would be something where we have an x squared term and an x term and a constant term. And we kind of have something similar going on. We do have a constant term, and instead of an x and an x squared, we have a something, in this case square root of x, and that same something that has been squared. If you were to square the square root of x, that would just give you x. So the idea is that if we were to substitute, if we said, well, if we say that u is equal to the square root of x, then squaring both sides, u squared should be the same thing as x. So you can transform it from something that wasn't quadratic into something that is. Now, the one caution here, of course, is when you solve the related equation, you'll find a value for u, but that, of course, is not the solution that you're looking for. The original equation was in terms of x, so you'll need to go back and find out what are the solutions in terms of x. We'll also need to keep in mind that, as always, if at any point we wind up squaring both sides of our equation, then we'll need to check our solutions. So let's do some solving. So as we said, the idea is that we are going to do a substitution here, letting u be equal to the square root of x, and that means that u squared would be the square root of x squared, which is the same thing as just x. So that we would have u squared minus 8u plus 15 equals to 0. And now we can solve by factoring if we want to. That factors nicely, u minus 3, u minus 5. And so we come up with u is equal to 3, or u is equal to 5. And we know what u is. U is the same thing as the square root of x. So the square root of x is 3, or the square root of x is 5. And that means then that x must either be 9 or x must be 25. And if we want to, we can go back and we can check our solutions and check to see that, yes, if you were to put 9 or 25 into this equation, it would make left side and right side equal to each other. So, for example, if you were to put in 9, you would have 9 minus 8 times the square root of 9, so 9 minus 8 times 3 plus 15. That adds up to 0. And same thing would be true with the 25. 25 minus 8 times the root of 25, 8 times 5, plus 15. Again, that also adds up to 0. So for both of these, left side and right side would be equal. We can say that our solution set contains two values, 9 and also 25. This one, if you wanted to, I mean, again, I'm presenting strategies and options and ways that you could think about solving this problem. And one way that you could try to solve it would be you could expand this out, rewrite it, bringing all of the x's to one side, and then trying to solve by factoring in some sort of a way. That may not be the best strategy here, because if you're thinking about expanding this out, you would get x to the 6 plus 3x, plus 2x cubed plus 1, 6x cubed and 6 and equal to 7. This is a polynomial where the highest power is x to the 6. You're not going to have an easy time factoring that. So maybe the better strategy would not be to expand, and this would be where you think about, well, could there be something else clever that I do to solve this? And you might notice that you do have, again, something and that same something that has been squared. So that if you were to let u replace that x cubed plus 1, then that means u squared would be the x cubed plus 1 squared. So really, this equation could be rewritten as u squared plus 6u equals to 7. And now you can just solve away however you'd like. Again, I'm leaving it open for however you might want to solve it. You can solve either by factoring or you can solve by quadratic formula, whatever you'd like to do at that point. So we come up with two values for u. Either u is -7 or it's equal to +1. And then, of course, don't forget we need to go back and find out what is our value for x. So u might be -7. That means that x cubed plus 1 is -7. Or x cubed is -8. Or x is the cube root of -8, which is -2. The other solution, if u is equal to 1, then x cubed plus 1 is equal to 1. That means that x cubed would be 0. And so x would be the cube root of 0, and roots of 0 is just 0. And for this, I can state my solutions then. I have two solutions, 0 and -2. And for this, again, you can check your solutions if you'd like, but for this, it's not mandatory. We didn't square both sides at any point during the procedure of this, so neither of these should be extraneous solutions. We can just continue and move on. All right, we've got another one to do here, and similar sort of thing as before. If you were to notice that this x minus 1 to the power of a quarter, that if you were to take x minus 1 to the quarter and square it, you would have x minus 1 to the power of a half. So we really do have, just as we did with the previous problem, we have something and that same something which has been squared. So if we were to replace x minus 1 to the quarter with u, then that means x minus 1 to the half would be u squared. So we would have u squared is equal to 12 minus u, or u squared plus u minus 12 is equal to 0. And then solving again, solving however you like, either by factoring or quadratic formula or whatever technique works best for you. In this case, factoring works really nicely. I find two solutions. U is -4, and I have u is equal to +3. And that gives me two potential solutions. Either x minus 1 to the quarter is -4, or x minus 1 to the quarter is equal to 3. And so now I just need to solve for x. So what I'll do is I'm going to raise both sides of this equation to the power of 4. Since it's a fourth root, then if I were to take both sides of the equation and raise it to the power of 4, that would get rid of that root. So I would have really just x minus 1 on the left side, and -4 to the power of 4 is 256. So we come up with one solution, or one potential solution rather, 257. And we'll do the same thing with the second possible solution. X minus 1 to the quarter is 3. If I were to take this equation and raise both sides to the power of 4, then that would give me x minus 1 is equal to 3 to the power of 4, which is 81. And so x is 82. Now, you might have caught me saying here potential solution, and you might be wondering, why did I say potential solution? And the reason for that is this. Remember that when we solve this, I said anytime you're solving an equation and you happen to raise both sides of an equation to an even power, that's a place where potentially you might have introduced an extraneous solution. So here, since I raised both sides of these equations to the power of 4, it's possible that I might wind up creating an extraneous solution. It's possible that one or both of these solutions might not solve the original equation. Now, I will say one thing before I do the checking of my solution, which is we probably should have noticed at here that there was a problem. In fact, we're going to see in the next slide that 257 will not be a solution after all. And the reason for that is, if you're thinking about what we had before we raised both sides to the power of 4, we had x minus 1 to the quarter is equal to negative 4. We had, in other words, the fourth root of something being a negative number. And one thing that we know is that for square roots, fourth roots, sixth roots, the only number that comes out of those is something that's positive. There really shouldn't be any number that when you take the square root of it, or fourth root of it, or sixth root of it, you would get a negative. So that being said, even though we now have probably reasoned out for ourselves why this should be not a solution of the original equation, we're still going to check our solutions just to demonstrate that. So when I check my solutions, I'm going to check again using the original equation, and I'll be substituting in 257 into the left side and the right side to see whether it makes the left side and the right side of the equation equal to each other or not. So that's what I'll do next. So if I'm checking x being 257, then on the left side I had x minus 1 to the power of a half, and on the right side I have 12 minus, that's my left side, and on my right side I had 12 minus x minus 1 to the quarter. So we'll see, do they make the left side and the right side equal to each other? Well, let's find out. On the left side, 257 plus 1 to the half, that's 256 to the power of a half, or square root of 256, which is 16. On the right side, you would have 12 minus 256 to the quarter, or fourth root of 256, which turns out to be 4. So we can see that the left side and the right side are not equal to each other, which means that we're going to reject x being 257. That is not a solution to the original equation. And we'll check the other solution, which was 82. So the left side would be 82 minus 1 to the half, or 81 to the half, square root of 81, which is just 9. And on the right side, we would have 12 minus 82 minus 1 to the quarter, or 12 minus fourth root of 81, which is 3. And now we can see that the left side and the right side are indeed equal to each other. So 82 is a solution. So the only solution to the original equation is 82. That 257 that we found, that was an extraneous solution. Again, with a lot of these problems, there's a couple of places where you might notice these things. So if we had noticed at this stage, we might have noticed that we had something in a fourth root equal to something negative, that there would be no way for that to happen. We might have stopped at that point and not found 257. We might have just said no solutions to that equation. But a nice thing to keep in mind, of course, is even if you didn't notice that, there's still the way to find out what's extraneous or not, and that's checking your solutions. And again, anytime you're raising both sides of the equation to an even power, That should be the warning bell that goes off in your mind that I need to check my solutions. All right, one last one for us to do here. And so for this one, I have something that's not a quadratic equation yet. And in fact, it could be turned into a quadratic equation with a little bit of algebra. I could, if I wanted to, multiply everybody on both sides of the equation by x squared, giving me 3 plus 14x equals 5x squared. Now, the one thing that I'll need to caution myself, of course, here is that for the original equation, there is an excluded value. X could not be equal to 0. That means that if we're solving this equation that we've just created, and if we find 0 as a solution, then we'll need to reject it. So let's start off with solving this equation. And again, you can solve by factoring, or you can solve in whatever way that you'd like. And for this, I solve by factoring. I'd be looking for numbers that multiply together to give me 5 times negative 3, which is negative 15. And the numbers that I'm looking for need to add up to negative 14. And so those two numbers would be negative 15 and positive 1. Okay, so from the first two terms, I'll factor out 5x, leaving x minus 3. From the next two terms, I want x minus 3 to be left behind, and I can make that happen by factoring out positive 1. Remember that you can always take out positive 1 or negative 1 as a common factor, and in this case, it's positive 1 is the thing that I need to factor out to leave x minus 3 behind. And so now I've come up with my solutions, 3 and negative a fifth. Now, neither of those are excluded, so there's no reason to believe that they're extraneous. We didn't square both sides of the equation at any point, so there's no reason to doubt either of those two solutions. So both of them, 3 and negative a fifth, should be the solutions to the original equation.